Hi, my name is Dr. Tishan, and we're going to solve some trig equations in this video. Please note that this video I am filming in my backyard, so there might be some background noises that I can't control. Nature has been a little bit loud this morning. There's airplanes flying overhead and so on. So if you hear any of that, just bear with me. It's just such a beautiful day out here, so I thought I would stream from out here. Okay, so we're going to solve trig equations, and you might want to have a unit circle handy unless you have your unit circle memorized. If you don't have it memorized, maybe you do, or maybe you just want to have it handy, but just find a unit circle somewhere. This is my trig reference sheet. Find a unit circle that you might be able to look up values. So let's look at our equations. We've got 4 trig equations total, 3 on the front board, there's 1 more on the back. So the first equation, and we're going to concentrate on sines and cosines, okay? So the first equation, we want to know sine x equals 1. So where on the unit circle is the sine of x equal to 1? On your unit circle, you have all these degree measures or radian measures, and each of these ordered pairs on the unit circle represent the location on the unit circle. So the x coordinate is the cosine of the angle, the y coordinate is the sine of the angle, if you remember that when you learned your unit circle. So we want to know where the sine of the angle is equal to 1, all right, and the sine is the y coordinate. So you look at all the ordered pairs on the unit circle, where is the y coordinate equal to 1? Right up here at pi over 2. And that's the only spot, isn't it? Okay, because over here on these axes, the sine is 0. Down here, 3 pi over 2, it's negative 1. So right up here at pi over 2. So where on the unit circle does our sine function equal 1? It happens when x is just pi over 2. You just have one answer in terms of what's on the unit circle. Now, sine equals pi over 2. Now, that is if we're only looking on the unit circle. That is in the interval of 0 to 2 pi. What if we want to represent the answer outside of the unit circle? Because realistically, these trig equations have infinitely many answers, okay? There's infinitely many places, infinitely many values we can substitute in for x to achieve this, make this a true equation. So sine equals 1. This is the spot on the unit circle where this sine is equal to 1, up here at pi over 2, okay? But if you add 2, if you go all the way around again and add 2 pi, 5 pi over 2 is another place where the sine equals 1. Add 2 pi again, you get 9 pi over 2. The sine of 9 pi over 2 is 1. Add 2 pi again, 13 pi over 2. The sine of 13 pi over 2, it's also 1. Add another 2 pi, so the sine of 17 pi over 2, it's also equal to 1. All those infinitely many places. And then go counterclockwise, go the other way. The sine of negative 3 pi over 2 equals 1. The sine of negative 7 pi over 2 equals 1. How would you represent all those infinitely many places? If you wanted to write a general solution to represent every value of x that satisfies this equation, how would we write this general solution? And I'll call it a general solution. So basically what you're going to do is you're going to take your pi over 2, okay, you're going to take your pi over 2 and you're going to add the complete rotation clockwise or counterclockwise around the circle, and clockwise, counterclockwise, we're talking 360 degrees, which in radians would be 2 pi radians. So we're going to add 2n pi, okay, where n is an integer, and your symbol for integer is this capital Z with a double bar, okay? An integer, which means if you take this expression and you let n equal negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, etc. in both directions, an integer, when you substitute those values in, you're going to generate, all right? So when n is equal to a negative 2, you get negative 7 pi over 2. The sine of negative 7 pi over 2 is 1. When n equals a negative 1, when you plug in negative 1 and evaluate this, you get negative 3 pi over 2, and the sine of negative 3 pi over 2 is 1. When n is 0, when n is 0, then you have pi over 2. We know the sine of pi over 2 is 1, okay? When n is 1, 2 pi plus pi over 2, that means x is 5 pi over 2. Sine of 5 pi over 2 is 1. All right, when n is 2, etc., it'll generate all the different values. So here is your general solution. This is the solution that encompasses all the infinitely many answers you would get for this, okay? So your trig, be careful when you're solving trig, right? Because if you're not working strictly within 0 to 2 pi, then you usually need to represent all the infinitely many answers that you get. Your trig equations generate infinitely many solutions, okay? Example number two is going to look just like example number one, but instead of sine x equals 1, what if it said the sine of 4x equals 1? Let's take a look at this, okay? It looks very similar, but let's see how we would kind of tweak it to answer this trig equation. Sine of 4x equals 1, and we want to know what is x to satisfy this, okay? So again, where on the unit circle do we have a sine equal to 1, all right? So your unit circle, remember that the sine of the angle is the y coordinate. And again, we're at pi over 2, aren't we? Okay, so we're at pi over 2. So, but how would you answer this, right? So see, the sine of the angle equals 1. When the angle is pi over 2, you get 1. So here the angle in our equation is x. We set x to pi over 2, but here the angle in our equation is 4x, okay? So when do we achieve a sine equal to 1? When the angle, which in this case is 4x, when the angle is pi over 2. Okay, so when the angle is pi over 2. All right, so your sine function equals 1 when the angle is pi over 2. Here x is pi over 2, but here you'd have to take the entire angle 4x and set the entire 4x equal to pi over 2. Okay, because that represents our angle. All right. And we don't want 4 times x, right? We just want to solve for x. So let's go ahead and divide both sides by 4 or multiply both sides by 1/4, whichever you prefer, and you end up with x equals pi over 8, okay? So pi over 8, and that would be our answer if we're looking 0 to 2 pi. But what if we wanted to represent this as a general solution, okay? So general solution, all the infinitely many. Remember with the 2 pi and what we had to do here, okay? So, but a little bit different how you will handle it when this is not just the plain old x here. A little bit different, okay? So let's go ahead. So what do we have here? We have the sine of 4x, okay, is equal to 1. And then let's go ahead and see how we would handle this. So when is this equal to 1? And we have already determined it's when 4x, okay, is equal to, well, we want the general solution, right? So this expression equals 1 when the angle is pi over 2 plus 2n pi, okay, because we're looking for the general solution. So when is the sine equal to 1? Sine equals 1 when the angle is pi over 2 any place, whether you go clockwise, counterclockwise, around the circle, that spot, okay? We don't want 4 times x, we just want x, so you got to take the left and the right side of the equations and multiply by 1/4 or divide both sides by 4, and so you end up with your general solution is going to be x, the 4's cancel, equals pi over 8, okay? Pi over 8 plus, and then 2 over 4, so that's going to be 1/2 n times pi, okay? And this is where n is an integer, okay? So n is an integer, all right? N is an element of the integers. N is going to be -3, -2, -1, 0, 1, 2, 3. So here's how you would handle if you do not have your plain old x, okay? So hopefully you see the strategy that you need in solving trig equations or wherever you're using this, okay? So that's what the strategy is, all right? So let's take a look at a couple more examples. A sine function here, and we'll have a cosine function on the backboard for example 4, but let's take a look, all right? So 2 times the sine x equals plus 1 equals 0. Here's example 3. We want to find all the angle measures that make this a true statement. So we're going to solve. We use algebraic thinking to solve, right? What do we have to do first? Well, every time you solve an equation, whatever kind of equation it is, you want to isolate the variable, wherever the variable is, right? We want to isolate the variable. So in this case, let's get that sine of x, that trig function by itself. To get the trig function by itself, we'll need to subtract 1 from both sides. Okay, so we'll subtract 1 from both sides of this equation. So subtract 1 from both sides. The left-hand side, you have 2 sine x. And the right-hand side, you have a -1. Okay, so we have a -1 here. All right, and then let's go ahead and divide both sides. Let's divide both sides by 2 because we want to isolate our trig function sine x. Divide by 2, the 2's cancel. So you have sine x equals a -1/2. All right, so now where on our unit circle do we have a y-coordinate, because we're still working with the sine function, so the sine function would be the y-coordinate. So where on the unit circle do we have a y-coordinate equal to a -1/2? Okay, so -1/2, you can see in the third and the fourth quadrants, you can see that your sine function, the y-coordinate, is a -1/2 at 7 pi over 6, and then over here at 11 pi over 6. So those are your values within the 0 to 2 pi, isn't it? So when is this a true statement? When x is equal to 7 pi over 6, when x is equal to 11 pi over 6. Okay, and this is when we're working in the interval 0 to 2 pi. All right, so this is in the interval 0 to 2 pi, and these would be your answers in the interval 0 to 2 pi. But what if you needed to produce a general solution? Okay, so what if you needed a general solution, not just in 0 to 2 pi? What would that look like, your general solution? So that would look like this. X is going to be 7 pi over 6, all right? Plus, you want to make sure that you're able to go all the way around, okay? So 2n pi. All right, you want to go ahead, you want all the infinitely many places, whether you travel clockwise or counterclockwise, okay? And we have another, so you have to also include 11 pi over 6 plus your 2n pi. All right, and keeping in mind that n is an element of, Greek letter epsilon means is an element of, so it's in the set of the integers, okay? So the integers, and there's your symbol, a lot of symbols here, but that's your notation. And here's your general solution for this. Remember, your trig equations generate infinitely many solutions, so you can't write infinitely many numbers down, so we need a way to kind of compact it and write it infinitely many solutions this way. All right, so 7 pi over 6, all those spots on the unit circle in the third quadrant, and then n equals -3, -2, -1, 0, 1, 2, 3, so clockwise or counterclockwise covers that third quadrant spot. And then 11 pi over 6, because fourth quadrant you have that spot also, and then this encompasses all the equivalent expressions there, okay? And then, so we have example number 4 next, and it's on the back board, so let me go ahead and flip the board to the back, okay? So we've got one more example to take a look at. And here it is. 2 sine squared x plus 3 cosine x minus 3 equals 0. Let's take a look at this example. This will be our last example in this video. So 2 sine squared x plus 3 cosine x minus 3. So what do we have going on here? We have sine squared. So you can see it encompasses a sine function and the cosine function. Well, we're not going to be able to solve it with a sine function and a cosine function, are we? Okay, so we want to write one of these in terms of the other. So what you want to do here is the sine squared, okay? Sine squared, we can write an equivalent expression for the sine squared utilizing Pythagorean identities, okay? So here's a trig function, a trig formula sheet here. Under Pythagorean identities, the sine squared x plus cosine squared x equals 1. So we're going to utilize that identity, and we're going to isolate the cosine squared, the sine squared. Okay, so sine squared, so if you isolate the sine squared, you can actually substitute in for sine squared 1 minus the cosine squared. So we're going to make that substitution using your trig Pythagorean identity right here. So you have 2, and then instead of sine squared, 1 minus cosine squared x, okay, plus 3 cosine x, and then minus 3. So the first thing we want to do, we want to write these trig functions. We want the same trig function, don't we? Okay, so utilize Pythagorean identity, rewrite sine squared x as 1 minus cosine squared x. Okay, then what do you see we need to do? Let's go ahead and distribute the 2. Let's go ahead, this is what I mean by nature. Okay, so bear with me, but let's go ahead and distribute the 2. Okay, so distribute the 2, so you have 2, all right, minus 2 cosine squared, distribute the 2, all right, plus 3 cosine x, and then minus 3. Okay, there we go. All right, so we have this when we distribute the 2. All right, let's collect like terms. All right, so we can combine the 2 and the negative 3. So let me bring this negative 2 cosine squared. I'm going to combine this at the end, plus 3 cosine x, and then subtract. So 2, and then take away 3, subtract 3 from 2, and you get negative 1. All right, so we're here. Now let's go ahead, and I like to, when I'm working with this expression with the quadratics, I like to have a leading coefficient on my x squared as a positive. I think it just might make it easier to see. So let's go ahead and divide every single term by a -1, so change in the sign. So we have a positive 2 cosine squared x, we have a minus 3 cosine x, and a plus 1. All right, so we have, it's a quadratic with a trig function. Your variable happens to be a trig function, but we're going to use the algebraic thinking that you would use to solve quadratic equations. We're going to solve this by factoring, and it is a quadratic form of a trig function. So we're going to solve by factoring because this trinomial is factorable. All right, so we'll solve by factoring. 2 cosine squared, how do I achieve that? Well, that's 2 cosine x times cosine x, isn't it? Okay, and we need to figure what two numbers have a product of +1 and a sum of -3. Actually, no, because we have the leading coefficient out front. So we just want to look, what two numbers have a product of +1? Well, you have 1 times 1 is 1, and we have -1 times -1. Those are the only two ways to get a product of +1. 1 times 1, -1 times -1. With a negative middle term, I'm going to need -1 times -1. This is the process here. All right, let's make sure it works. So 2 cosine x times cosine x gives us our cosine squared. Distribute, so -2 cosine x's and a -1 cosine x's. There's my -3, and -1 times -1 is 1, okay? Now we have the product of two factors. When is the product of two factors equal to 0? Anytime you take two things and multiply them, when do you get 0? When either factor is 0, right? When this factor 0 times something is 0, or something times 0 is 0, when either factor is 0. So the next step you want to do is take each factor, the 2 cosine x minus 1, set each factor equal to 0, and the cosine x minus 1. Set each factor equal to 0. All right, and solve. So here on this side, you're going to add 1 to both sides, divide by 2, so your cosine x is going to be a positive 1/2. All right, and so where on the unit circle is your x coordinate, right? It's the cosine. Where on your unit circle is the x coordinate of positive 1/2, okay? That's going to happen at pi over 3 and at 5 pi over 3. So when x is pi over 3 and when x is 5 pi over 3. Okay, so that's where your cosine function is equal to a 1/2. All right, come on over here. Let's solve this. We got to solve this side too. So let's solve this side. Add 1 to both sides. Cosine x, right, equals 1. Where on your unit circle is the cosine function equal to 1, a positive 1? That's going to happen at 0 radians, 0 degrees, 0 radians. That happens when x is 0. Okay, so these are the spots on your unit circle. These are the answers that you get that are in your interval of 0 to 2 pi. Okay, so these are the answers that are in 0 to 2 pi. Okay, so we're here. What if we want to write a general solution for, because these trig equations, we have infinitely many solutions. So what if we would need to represent all the infinitely many solutions and not just the solutions from 0 to 2 pi? Okay, so we want to write a general solution. I have space here, so I've got a little bit over here. So let's write the general solution over here. So our general solution, so what do we have? We have pi over 3, okay? And we have to add the 2n pi to that, okay? We have 5 pi over 3. We have to add 2n pi to that, okay? And we have 0, that it counts, okay? We have to add 2n pi to that as well, okay? And so, and all the while n is an integer, okay? So you're going to plug in the -3, -2, -1, 0, 1, 2, 3 into these expressions, and this is how you will be able to generate the infinitely many ways of expressing your solution to this equation. Okay, so I hope this helps with solving equations. Thank you so much for your patience with background noise. I just love doing this from outside. It's just beautiful out here. So I hope this helps, and thank you for watching. I appreciate it so much. Best wishes to all of you. Thank you. Bye-bye.